He was to be funded by the Navy on more like humanoids, but he requested to work on projects that he was more interested in. We were not necessarily the expertise of the lab. In particular, he brought a first project on active perception, in the sense of finding configurations of the robot in order to find an object better. And you know, I gave him green light to work on these projects, and pretty much that have been sort of a determinant of his PhD. Minkyu has been sort of creating new projects as along and pursuing them. So the next project he worked on was on finding partially hidden, fully or partially hidden objects using a combination of particle filters and information gain based optimization. He worked on person following, and in particular, what strategies could be useful if a person, if we lose the person, we have partial information of where the person went. And that brought him to the use of context. You know, if you don't have observations, or you don't have kind of camera observations, can you have some sort of other observations based on predictions of the context? And then he expanded this work with people awareness, navigation, taking into account the awareness of people of robots being on the environment. And that was sort of the first part of his first papers. And Army Futures Command came in a couple of years ago, 2.5 years, and Minkyu was the first guy to be supported by this funding. In particular, in the area that was part of the proposal Army Futures Command of using multiple robots to search for objects. And he approached this problem as also an information gain optimization method, and he found some limitations of inefficiency of the coverage area. And then most recently, and almost his last work has been on multi-robot search using clustering techniques, and he has shown that this is much more effective than other methods. And finally, with and by the way, he has used extensively software from Professor Biswas on localization and multi-robot communications, and then and also most recently with Professor Pryor. He has worked extensively on with Chris and Blake, Blake Anderson. They have worked on taking these algorithms for outdoor search, which has a whole lot of new difficulties, and they have succeeded with some partial results as well. So that's all for now, and let's have Minkyu. We will have a presentation for about 45 minutes. And then we're going to go with audience questions, and then we'll ask the audience to leave, and then we'll go into faculty committee questions. Anybody has any comment before we start? All right, fire it up, Minkyu, all yours.
Okay, thank you for a great introduction. Welcome to my dissertation presentation. Thank you so much for being here today. I'm Minkyu Kim. I belong to the Human Centered Robotics Laboratory. As you know, my advisor is Luis Santis. So today I will present my dissertation work, which summarizes my research work over the past 6 years. So my research presentation title is Toward the Intelligent and Reliable Robot Behaviors for Human-Centered Autonomy. Let me briefly talk about my background. I got bachelor's and master's degree in mechanical engineering. After graduation, I worked as a research scientist in South Korea National Research Institute. At that time, my research focused on wearable sensors, teleoperation, and rehabilitation robotics. In 2016, I came to USA and started a PhD study, joining the Human-Centered Robotics Laboratory. After that, after I joined, fortunately, I had opportunities to participate in the global robot competition called RoboCup at Home in years 2017 and 2018. I started my journey with autonomous robot with this competition. So in 2017, we won a third prize for the competition in Japan. So while preparing for this competition, I was exposed to the task, including some navigation and person following and object manipulation. So after the competition, I was inspired to further research and improve both cognitive and control aspects of robots to support the human. Nowadays, with the development of sensors and actuation, machine learning algorithm, and etc., it has become possible for robots to perform increasingly in diverse and complex tasks. Therefore, autonomous robots can be easily found in many industrial places, such as in supply chains, in factories, warehouse, or last mile delivery application. And perception and planning and control are two essential capabilities for autonomous robots. Generally speaking, a given task, perception enables robots to understand the environment, while planning and control allows robots to make a smart decision and to accomplish a mission with desired behavior. In near future, as we know already, robots will increasingly interact, explore, and cooperate with people. Even though there have been many studies regarding some motion planning or control method for robust and intelligent decision making is essential for robots to coexist with the human. In particular, a capable decision making and control framework should incorporate more and more aspects of human behavior and their human state. So through my robotics career, the most rewarding part of being a robotic engineer is when I developed some robotics capability to benefit humans. So therefore, my research aims to build some smart autonomous robot or developing robotics new capabilities for supporting human. So in this context, human-centered autonomy has become my research theme. To be more specific, I have focused on devising capabilities for autonomous robot operating in human environment. In the last few years, I have focused on some topics of social navigation, navigation with crowd, and person following, active object tracking, and the multi-robot target search. First of all, a human-centered autonomy should not damage human. We need to guarantee the safety issue. In addition, it should be able to give some people a sense of comfort from the point of view of cognitive interaction. Also, there are many uncertainties when humans are involved in a task, and the robot must have the robustness and flexibility to deal with this. So in this dissertation, I have focused on developing some intelligent and reliable autonomous robot for human. The work present in this dissertation has 3 parts, and those are social navigation, active sensing, and multi-robot target search. So let's move on to the first topic, social navigation based on people's awareness robot. Let's consider the situation in this figure with one person on a bicycle riding and a couple that is walking toward the robot and the final person walking near the robot. So who do you think poses the highest risk to the robot? Which of these people should be more concerning in terms of safety? So I think the answer is that it might be the person that is least aware of the robot, since in such case, the situation could result on an accidental collision. So another remark is that when people navigate, when people walk, they behave differently depending on their awareness of each other. So for example, when two people cross paths, if those people are aware of each other or are aware of nearby robot, then it is assumed that they will safely avoid each other. So overall, the idea is robot navigation could benefit if robot knows whether people are aware of them or not. Therefore, what we studied consists on allowing robots to navigate closely to pedestrians who are aware of them and far from those who are not aware of the robot. Yeah, our contribution is to incorporate this awareness model when robots navigate around the humans. In our framework, navigation consists of global and local planner, and then global path is obtained using MDP-based path planning algorithm. And the gaze model is incorporated into the local planner to decide whether to keep the robot moving following the global path or replan it. And the local planner is implemented using partially observable Markov decision processes. The reason we are using it is that it's not possible to detect the precisely human's awareness like by detecting the gaze. Based on the robot's position and dynamic obstacles and predicted human awareness, the local planner will decide the robot's policy consisting the instructions such as go, stop, and avoid. Here is our PUMDP formulation. We design state for the robot and the pedestrian, where the pedestrian state contain their position and goal position and the awareness model. Observation contains 2D position of the human and gaze information. We tested our proposed approach in both simulation and real-world environment. So for real-world deployment, we use Toyota HSR mobile robot. And to detect people, we use the YOLO algorithm to detect people. So here is a quick view of the simulation result in the grid wall setting. In this example, there are 3 pedestrians, and blue triangle and red circles are robot-aware pedestrian, while green crosses represent non-robot-aware pedestrians. So the robot position is described as a black star point. And then let's go to the time equal 11 here. And then robot was able to go forward because it believed that the blue triangle and the red ball will not interfere with its path since they correspond to the robot-aware pedestrian. So they believe the pedestrians are aware of the robot. On the other hand, at the next time step, the green pedestrian comes nearby to its path. And in this case, the robot cannot go forward because the green pedestrian is not aware of the robot. Then robot chooses the wait action at this moment. And then after that, after the green pedestrian moves away, then the robot was able to continue on the path toward the goal point. So this example validate that our proposed algorithm could generate the proper social navigation using some people awareness model. And then here we introduce the awareness model for real-world implementation. We employ the binary awareness variable, which is calculated using the human gaze detection model. So here we define the center region for the gaze and check whether the human's gaze in this region or not. So yeah, if the robot can detect the human gaze for some amount of time, the awareness variable will be set to true. So here we set 3 seconds as a threshold for our experiment. So here's a video in old WRW building in UT. And then, so I use the HSR. So if the robot can sense the human's eyes, we can see like a human's eye here. using some face recognition and gaze detection. And if so, myself, the first pedestrian was recognized as a being aware of the robot. So it can just go like aggressively. And then after it's following, it's like a global path through this here. And then the second group of people talking to each other at the corridor, they are now looking at the robot, and therefore they are like labeled as not aware pedestrians. So in that case, the robot will handle the situation conservatively by stopping and waiting, and then robot is prompt to find another way to avoid this group to reach the goal position. The experiment confirms that the robot was able to navigate near people only when they are robot aware. So we measure the distance between the group of aware, like pedestrian and non-aware pedestrian. So this right figure shows that the robot was able to get closer to the robot aware pedestrian about 1 meter. Then the next topic focuses on some deep reinforcement learning to learn a navigation strategy in very crowded environment. So as shown in this video, when human walk, self-organization behavior can be observed. So this can be shown in like a black and red color here. And lane formation is a result of the human self-organizing behavior, which are known to use least effort to avoid collision while not disrupting the overall navigation flow. In addition, we found the fact that the following is one of the important factors in the pedestrian self-organizing phenomenon. Our goal here is to learn this kind of behavior when robot navigates in dense human environment using end-to-end model-free deep reinforcement learning. So I will briefly explain our proposed method. The left upper figure in this mosaic figure mimics a real-world situation. So it's in the gazebo simulation environment, but and then we would like to simplify this scene, and then the right bottom figure is an example of our input for learning. So we use this image as such kind of input, allows more flexibility for dynamic situation. The pixel-based approach have been proven successful for many reinforcement applications. So we use like a pixel because we don't have to take care of like the change of dimension and its efficiency. Like the feature dimension is already fixed. Our real-world model takes into account the goal position, collisions, and some navigation efficiency. And then to evaluate the resulting navigation policy, we are considering using 5 different metrics. And then we need to simulate the group behavior to make a pedestrian moving. So we use some extended social force model, which incorporates a group behavior. This model contains some additional term regarding group force model. And then this group force model includes some attractive force and repulsive force and the force regarding the gaze. Here's our proposed learning architecture, which uses some actor critic with autoencoder. In this framework, the actor aims to maximize the expected reward while also maximizing entropy. And then we stack like 3 consecutive images so that the policy can be aware of the position or velocity of the pedestrian. In addition to image, we provide input data with information on the goal and the current velocity of the robot. So here are preliminary results. The robot is in this red dot, and then the goal is described in the green dot. There are like individual pedestrian and several groups are described in the gray region. And these preliminary results show like efficient navigation performance in like two different situations, including just hallway and then doorway. We are still iterating reward function and input vector for the further improvement. So this setting was fully observable, and we try to use a partially observable case. So what we are doing is we are using use like a scale type of FOB, or use this kind of like a laser scan with 5-meter range. So we are still debugging our learning architecture and reward function to obtain stable navigation performance. And then we are preparing this result to submit to target for the ICRA submission, which is next month. Okay, and the third topic consists of person following using active search. So this work was motivated from one of the tasks in the robot cup at home competition. The task of robot is to follow the human target in indoor environment. So unfortunately, following often fails since human can move very fast or occlusion might occur during following. So we assume that if robot has some active capability to re-identify a target after losing them, following behavior could become more robust. So recovery behavior in this study consists on some turning robot's head around and moving to the location where the target might be found again. We use like two different prediction model, like a human trajectory prediction and map location prediction. And to identify the target, some sensor fusion, high-level sensor fusion technique was used. To make the robot fully autonomous, a behavior tree was used. So this structure is very similar to the hierarchical state machine. This can be used to design some desired set of behavior patterns. Like this allows the actions to be executed sequentially and repeatedly according to the condition. So the basic strategy here is the following. So when a robot is able to see a target, the robot should be able to track and follow the target. If the target is missing, the robot is supposed to find it by moving its head. And if target is still missing, the robot will navigate toward its predicted location. And then after that, if the target is still missing, the final strategy is heading to other map location, which are computed using our map location prediction algorithm. So, and then person following requires people detection and person identification. So to do so, we use we combine 2D LiDAR sensing and the IGBT image image information. To detect the people, we use laser based lag detector and then open pose. And to identify specific target, we use some face recognition and close recognition algorithm. So one good advantage of using open pose is that it provides the skeleton joint information. As you can see in the right bottom figure, it can give some skeleton joint information for a detected person. So using this information, we can extract the green box, which is regarding the upper body shirts. So we use like a 2, 5, 8, 11 joint to define this area, and then we are extracting the color information within this box. And then comparing this color with trained feature, the close recognition algorithm can be applied. So when a robot tries to identify or re-identify the target, the robot sequentially tracks the high-level recognition result in the order of the importance. For example, the face is the most important feature of the target. So we check the face first and then followed with the close comparison. So yeah, our proposed flow chart follow the logic in this figure, and then check those features sequentially. In this slide, I will briefly explain our map representation. We assume that the robot is aware of some boundary information here and then connectivity. These allow us to robot to be aware where the person might be located and also reason about where they are heading to. Yeah, I'm gonna skip this. And then this slide shows our framework can predict some possible location of the human target. So this prediction is designed for overcoming edge cases, such as target suddenly disappearing after passing a doorway or turning their direction near like a static obstacles. So to predict people trajectory, we utilize a support vector regression technique based on some observed trajectory of the human target. So we note that our SVR based trajectory outperform the prediction based on polynomial regression. And on the other hand, we also predict what map location the person is heading to. So the basic idea is simple. We compute the change of the distance among connected regions from the current location. And this information provides a metric where the target is heading. So therefore, if the target disappears, the robot can use the prediction of the map location the person was heading to. Yeah, so here's the video showcasing a person following. This video was taken in AHG, very old AHG. So it's following me. And then if the target is missing here, target is lost, it will go to the predicted location using our predicted algorithm. And then it is searching for the target. And if there's no target, it is supposed to go to the map location. Once the target is found, and then it will follow again, and then to identify target, we can check like the confidence of the close here, close recognition, also face. So as shown here, the robot successfully followed the target myself in this indoor environment. Yeah, we tested this following behavior in our current ASB building, our laboratory. So I assume that this laboratory is more crowded at the time of the recording, and then it also has some corridor. So overall, I tested many like different scenarios, starting at different position and traveling different routes. Yes. Yeah, I can just skip that. So yeah, it was able to follow the person target. And then, so yeah, we can analyze like a person following behavior. So the left figure shows the information timeline. We computed distance between the target and robot, and the target visibility, loom location, and so on. And then we can see what robot, which decision was made by robot for each time step, for each situation. Okay, and the next topic concerns the active object tracking using context estimation. So here the active means that the tracking system is able to perform some target recovery behavior when targets are occluded or missing. So this is really similar to the approach for the person following. And this work is related to the mobile sensor location or viewpoint planning or active perception. The main question is what a robot should do when the target goes missing during the tracking. So one key consideration I used for this was to reason about the situational context in order to improve the target estimation. So to do so, I propose to use some domain knowledge in this framework. And then if we assume that there exists a finite discrete number of context situations, such as target is visible, occluded, and disappeared or irrecoverable, then to estimate the target location, we firstly estimate the context, and then we can infer the target location from that context. So this approach can be realized by dynamic Bayesian network and performed using some particle filter with the PUMDP formulation. So here are the details of the proposed dynamic Bayesian network. So in contrast to the classical Bayesian network, which usually have X, like a target state X and the observation Z, in our method, we incorporate the context variable C here. And then C is the belief of the context at time. CK is the belief of the context at the time K. So for example, it could be we can have the belief of context as missing, like a disappeared with 70% probability or occluded with 20% probability, and target is visible like a 5% probability, and irrecoverable state with a 5 probability. And yeah, so as shown in the last equation on the right bottom side here, we estimate the current target location based on some weighted sum of the hybrid motion model as a function of their context. So therefore, mu I and sigma I are the estimate target location or motion model from the I's context, and we are making some Gaussian mixture model to estimate the target location. Yeah, as mentioned before, we use like Gaussian distribution, and for each context, we have like hybrid motion model. I'm gonna skip this. We also employ a PUMDP as a high-level planner to estimate context and find proper actions based on these states. As I explained before, we have 4 context states: visible, like disappeared, occluded, irrecoverable, and then we have some transition diagram between these context states. We have 3 different actions: track, search, and active move, and we define 4 observation features consisting on some target existence, overlap ratio between the object obtained from the image, and the change of the depth of the target, and whether humans are present around the target. So using this observation, we are estimating the current context. Also, yes, so yeah. So in this study, we utilize the online PUMDP server, which is called Despot, determines sparse partially observed tree to obtain the optimal action policy based on the context belief state. Now, this is how our robot finds an optimal configuration when high-level planner decides to active move. So in order to relocate the target X, we have to maximize the information gain using the expected configuration Q. So the robot should find the configuration that can reduce the uncertainty of the target location given its field of view. In this figure, the field of view is shown as a blue region. And then since we are using particle filtering, the particles will be sampled around the target location. If target is like occluded by another object like this, then some particle will be seen like in this orange, but others will not. So based on this visibility information, particles can be divided into two sets, like S1 and S2. And then we can define the information gain given this, given the importance of particle here to take advantage of the particle filters. Then we can sample some possible configuration around the current position. And then for each configuration, we can compute the expected information gain with these like a particle. So these are like a expected information gain given the expected robot configuration, QK. So with this utility, we formulate the optimal control problem, which uses like a information gain and penalize the traveling cost and perception cost. So the traveling cost computes the distance between the current configuration and the next configuration, while the perception cost calculate the distance between the target object and the next configuration. And such process defines the movement of the robot in order to efficiently find the desired target object. Yeah, here's the video of the active object tracking method. In this video, like a bottle is a target, and the green ball depicts the estimate location of the target. So yeah, I occluded the target, and the robot sampled like a possible configuration, which can be described in the red small arrows, and was able to find the next configuration so that we can refine the bottle here, and then the target is visible again. So yeah, so based on the situation, the robot can follow the target like a visual servoing, because the target is in the image frame, so it is trying to get the target in the image frame, and then I'm gonna try to occlude this again, and the robot was able to find the another configuration to recover the target tracking here. And then the second scenario involves some human. I just came here, like I moved target away, somewhere far from the robot, and given our framework, the robot strategy determined is to find the nearby human first and look for the target near that human. Because we use the assumption that only a human can move the target object, so naturally finding human first is intuitive strategy for the find the target. So to evaluate tracking performance, we propose like 4 different criteria: success ratio, tracking ratio, average restoring time, failure time. Yeah, but I can skip this one. So yeah, the next topic concerns the design of the path planning algorithm for multi-robot system that can autonomously search for target in complex environment. So we propose some leader-follower hierarchical decision-making structure, which generate the path for agent sequentially using some information theoretic utility function. Yeah, so here's a sketch of the simulation environment. They're like a robot, and then we are generating some candidates of trajectory, like a global path trajectory and the local trajectory. So among these candidates, our sampling-based optimization will find the best one based on the information theoretic utility function. Then we have to evaluate each candidate trajectory based on expected information gain. So we sample several trajectory, and then we can have some point, and then we can calculate the expected information gain within this field of view. So using occupancy grid map representation, the information gain becomes proportional to the number of uncovered cells that can be covered based on the robot's field of view. Though before this evaluation, when we sample the paths are reparameterized with respect to their arc length as a normalizing process to manage some heterogeneity of the moving speed. Yeah, here we propose either follow or hierarchy setting in which we assume that first agent is the leader and the second is the sub-leader and consisting of sequentially lowercase followers. By using this decision-making structure, we can save some computational costs, and then we can scale up to many different agent robot teams. So here's a short video with a simulation environment. Left upper part show the two robots navigating here, and this is like a one sensor view from one agent, and we are sampling the trajectory, and the blue one is selected one, and this is the entropy map. So once the robot covers this area, the red area will disappear, and then it will be filled with the white area, which means this area is covered. And then, yeah, we tested several different initial conditions, and yeah, we verified it's working. And also we tested with different number of agents, up to 10 agents. And also we tested with some one-time search and continuous search by adding some time-varying characteristic to the entropy map. So this is the video of using two robots in AHG environments. So we have the HSR and we have A1 here. So, you know, the yellows are covered area, and then they are choosing the next waypoint for each step so that it can cover all the search region until the target is found. So yeah. So I will just skip this. So we use the YOLO to detect the human. So this is the YOLO for A1. This is YOLO for HSR. And the search was done once it found the target here. But here actually, oh, sorry. So the following figure shows the search trajectory. And then the main limitation is that we cannot guarantee the complete coverage, and we cannot expect the path to be optimal, resulting in robots going back and forth like this. And then for some previous visit paths. So this limitation prompted us to develop a much more efficient method, which I will describe the next. So here we propose another search algorithm. Some key difference is we are taking advantage on knowledge of their heterogeneous difference, and we aims to guarantee the complete coverage. So we manage heterogeneity by defining using coverage competency, which we define as a normalized parameter, which represents the combination of the sensor range and the robot's traveling speed. Our main contribution is we propose the coverage competency and waypoint allocation factor, and then we show that our algorithm outperforms one of the state-of-the-art coverage path planning algorithm by 10% in coverage completion time. Yes, so we firstly define the coverage competency for each robot. So search capability can be computed with multiplication of sensing range and moving speed, and then we are normalizing this value. And this vector will be used to assign the waypoint. So using this vector, we do the heterogeneous clustering. So faster agent is supposed to get more clustered than the slower agent, since it can travel further away. And then next, we define the waypoint allocation factor to evaluate how well we are allocating waypoints to the robot network To do that, we calculate the standard deviation between the swept area for every agent and their coverage competency, normalize the factor lambda here. So yeah, I will briefly explain. So suppose we have two robots with the same sensing range, with one then being twice faster than the other one. Then the faster agent has smaller eta value here. And then let's say the covered area is 10 and 5 for each agent. Then this value become the same, which means the search task is distributed evenly, incorporating some heterogeneity of the each individual robot characteristic. So as such, this waypoint allocation factor will be virtually zero, meaning that the algorithm has assigned optimally the coverage. So here's our method overview. So we assume that the search region is defined, and then we we generate waypoints incorporating some field of view size over the unexplored region. And then we assume that visiting this waypoint will provide a complete coverage. And next waypoint are clustered using our proposed heterogeneous clustering method. And then each cluster is assigned to each agent. And after clustering, we are solving traveling salesman problem over the cluster, get an optimal route for each agent. And then, there are like several replanning conditions, which is robot failure and new target information is obtained, and some agents complete their search faster than expected. We just repeat the step from 2 to 5 to regenerate the waypoint and reassign the cluster and regenerate the path plan. To validate our algorithm, numerical simulation with Python were tested. And then we can show like our algorithm was scalable up to 50 agents. And then also we can show that our algorithm can have recovery behavior when robot failed here in simulation. To validate the proposed algorithm, we have compared our approach with another state-of-the-art search algorithm called SCOPP, which is published in 2021 ICRA. And then we used the scenario with 13 agents and 10 trier over the same search area. All agents have some speed 4 meters per second. And then, overall, our algorithm was able to show better performance by 10% for homogeneous teams. And then we also test coverage competency, improve the waypoint allocation factor by a significant factor, especially as a team size increase. So this blue describe without coverage competency, and this black line describe the case when incorporating the coverage competency, which means that our algorithm can effectively use the heterogeneity of the robot teams. To implement this method in real-world scenario, we add one more robot. So we use one HSR robot and 2 Unitree A1 quadrop robot. So each robot has their independent perception and navigation and send this localization information. And our search server provides search paths for each agent. This is like the snapshot of the search experiment, which is done in ASE 4th floor. So I will just show the video here. So target was valuable. So here we can see 3 robots are moving, and when we can see RBs, they have like a field of view, scale type of field of view, and then similar to the previous experiments, they are covering the yellow area to search. Oh, I think internet is a little bit slow. Yeah, sorry. Yeah, we can just remind. So yeah, we use localization as a ENML, which is developed by the Jody Biswas here. So thanks for developing such a good localization algorithm. So we use the YOLO for here to just detect the sports ball. So and then it was stopped here. And we did many simulation in gazebo environment for mimicking the search and rescue mission. So I'm gonna just skip this one. So more recently, we have collaborated work with the group of the Mitch Pryor, especially with the Chris Suarez and Rupert Blake Anderson. So yeah, and also my teammate Ryan Gupta. So we use our visual information here, not using LiDAR, but use like a visual information. So we were able to perform some efficient coverage in this outdoor setup on the back of a nice robotics building, demonstrating a proof of implementation in diverse environments. We have used the clear path Jakar and then the Walrus robot developed from their group here. So yeah, we are currently working on improved robustness and other optimization. Also, in the future, we would like to improve the networking issue, which have limited the scope of this project. And I believe Ryan will continue working on this project alongside the new student joining the HCRL. So yeah. Okay, so I think I can skip this one. This was used for localizing the target, but I think it's not that important. So once again, here's the summary of my work, including social navigation, active sensing, and multi-robot target search. For the next career, I would like to exploit my knowledge and research experience to build new robotic system or develop new capability of robot to support the human. I will continue focusing at the intersection of perception and planning and human-robot interaction. Now I'm gonna work with the Astro indoor robot from the Amazon. So here's my current publication list so far. And then I think this is the last slide. Thank you for listening my presentation. If you have any question, feel free to ask. And thank you again.